Okay, so today I wanted to give you guys some additional examples of probabilities. So I have about 6 of them here that I will go through. So the first one is an example of sample space. So the sample space is a list of all possible outcomes. So if we want to find the sample space for tossing a 6-sided die twice and then recording the sum, your first step is just to see, well, how many possibilities do you have so that you can make sure that you have listed all of them. So we do this by the counting principle. So we're tossing a dice twice, so we've got 2 choices or 2 spots there that we're filling. And we have 6 choices because there are 6 sides to a dice. So there's 6, and then we're tossing a second time, so there's 6 second toss. So when you multiply those together, there are 36 different possibilities if you write down all of the possible ways you can do this. So your second step would be to list the sample space for doing this. So that would be listing all of the different possibilities. Then once you do that, you need to then find the sum of each of those possibilities because we're tossing a 6-sided die twice and then recording the sum. So then you need to actually find the sum in order to create the sample space for the actual event that they're giving you. Now, for a problem like this, if you're adding up your numbers, you know that, okay, if you add the lowest numbers up, 1 plus 1 is going to be 2, and you add the highest number, 6 and 6 is 12. So you know that your numbers have to add up. They're going to add up between 2 and 12. So we don't have to actually list everything. So I'm going to we know that all of these numbers that add up together have to be between 2 and 12. But you can list them out and then do the addition. In some cases, you would have to do that because depending on what it's asking for, how many numbers you have, that sort of thing. So I actually went and I wrote some computer code. This is in a programming language called Mathematica, which is designed with a lot of structures to help you do things easier. And so I created my 2 events. First toss is A, the second toss is B. And then we're looking at the sum of those. So I basically told it, create me a table where you're going through all those choices and adding them together. So you can see that I have 36 choices here, as we found that there's 36 possibilities. And I had to do the sum right away. So it's just listed me the sum of all the different possibilities. So you can see the lowest number is 2, the highest number is 12. When you're writing sample space, you don't write repeats. So you would just be looking at your table and then writing all of the numbers that show up. And so this would be the same as what we saw before. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So you don't have to use code to do this. I just wanted to show an example of how you could if you're inclined to do that and you don't want to try to write them by hand. So just an option there, just showing you how I did that. Now here's another example of sample space. So we want to find the sample space for selecting 2 marbles without replacement, which means that once you remove a marble, you're not putting it back in. From a bag containing 2 marbles, 2 blue marbles, and 1 yellow marble. So this one, we can't just do what we did before because we're removing marbles. And then we are going to have where the order of these is not going to matter when we're looking at the sample space. So we're going to just consider whether you have a blue and a red and a blue, you still have 1 of each. And so the order there is not going to matter. So this is a different method than example 1, where you then actually had to do some addition there. So here, we're just looking at what our possibilities are. So if we have 2 red, 2 blue, 1 yellow, that gives us 5 marbles. And so we're doing it without replacement. So you're going to pick a marble, and then you have 4 choices remaining. This one's easy enough to write down by hand. So let's say I pick a red marble. Then from there, I could have another red marble because there's 2 of them. Or I can have a red marble and then pick a marble. Or I could have a red marble and pick a yellow marble. Now, since there's 2 blue marbles, I could basically have the second blue marble, but those are going to be considered the same. It's just a red and a blue marble. There's no difference between the 2 different blue marbles. Then we can say, well, what if I pick a blue marble first? So I could pick a blue marble and then a red, and because there's two red marbles, you can think of that as, okay, a blue and a red, and the other red. There are two blue marbles, so I can have a blue and then I can have another blue marble. There's only one yellow marble, so that would be blue and a yellow. Now let's say you pick a yellow marble, so you can have a yellow and then a red, and since there's two reds, you can list those separately. Or you can pick blues. You can have a yellow and a blue. There's only one yellow, so you can't pick another yellow. So now a lot of these are basically identical choices, and so like a yellow and a red, there's no difference between the two different choices. And the order here doesn't matter because you're still going to have a yellow and a red or a red and a yellow. The order there doesn't matter. So you're just looking at how many different distinct possibilities are there to get the sample space. And so this in set notation, so we've got a red and a red, and then a red and a blue, and a red and a yellow. If I look at my next one, I had a blue and a red, but that's the same as red and blue. But then I have a blue and a blue, and then a blue and a yellow. And then you have yellow red, which is the same as red yellow, yellow blue, which is the same as blue yellow. So actually you don't have any additional possibilities. And so that is our sample space here. So we have 5 different possibilities in our sample space. We're not doing replacement. If you did replacement, then it would be even more complicated, because then you could have a yellow, and you actually then have more blue-red combinations, that sort of thing. Now, I actually went through just for kicks to, again, just to code that. And so you can see all the different possibilities if you're not worrying about the order. And, if you're actually thinking, okay, one blue is different from another blue, this actually would not count. This would be with replacement, what I did right here. Because you would be assuming you'd be putting your blue back in, but, you can still use to see the different combinations. So you can still say, okay, well, even if the one thing that's with replacement, I can't have a yellow and a yellow. That's the only thing that would be affected, because we still have 2 reds, 2 blues, so you still can't have a red and a blue blue. So that is the only one that if you did it without replacement that you would not be able to write down, because we don't have 2 yellows to choose from. So once you remove it, you don't have it anymore. So sample space here, and we're going to do the without replacement. I'm just going to write down we have a red and a red. I'm going to go across red, blue, red, yellow. I'm just going straight across. And then next one that's unique is a blue, blue, and let's see, blue, yellow, and then everything else we already have listed. So that's another way to do it. You just have to keep in mind that if you wrote some code to just go through all the different possibilities, with replacement has some things that you may not get if you did it without replacement, based off of how many marbles you have for each color. So you do have to think about that. So things like this, it's, if you don't have the same number of each thing, like we didn't just have 2 reds, 2 blues, 2 yellows, we actually have different numbers of marbles. It makes it a little more complicated. Okay, so next example is actually find some probabilities. So you toss a coin 3 times, find the probability of getting a tail on the last toss. So we've got, when you toss a coin, 2 choices, heads or tails. So we're going to just look at how many choices that we have here. We're doing this 3 times. So 2, 2, and 2. So that is going to be 8 options. So I should have 8 things written down. Next step would be to find the sample space. And so this one, there's only 8 things. It's easy enough to, write. See, I could get heads all 3 times. I could have heads, heads, tail. Or maybe I get heads, tail, heads, or a tail and then 2 heads. So those are all the different possibilities if I had 2 heads and a tail. Or what if I had 1 head and 2 tails. So I can just shift where the head is. And those give me all those possibilities. And then I could have all tails. So you count these up, there are 8 of them, so that is the whole sample space. We'd normally write this in a nice long line, but I'm going to we're going to just have this formatted differently. You get the idea, though. They'd be all in a set, basically. Now we want to know how many of those actually fit our probability. We want to get a tail on the last toss. So I'm going to highlight those. So you can see that there are 4 of them that have a tail in the last toss, and we have 8 options. So there are 4 that match our event. So the probability would be 4 out of 8 total, which is equal to 1/2. And that makes sense because that last toss could either be heads or tails. It actually doesn't really matter what the first 2 tosses is, because all we care about is getting a tail in the last toss. Now, if it asked about the probability of getting a tail in the last 2 tosses, then that would be different, and we would have 2 out of 8 there, and that would be 1/4, which is actually the probability of 1/2 times 1/2. So you can multiply probabilities in this case, and that is because these are independent events. Independent events means the probability does not affect the probability of the second. So because tossing 1 coin doesn't affect your probability for tossing the second or the third, you can multiply your probabilities in this case. I'm going to talk about independent events a little bit later in example 5. So example 4 here, what happens if we have events that share a sample space? So if you roll a fair die, what is the probability of rolling a prime number and a multiple of 3? So these share a sample space because a multiple of 3 also, like 3 is a multiple of 3 and it's a prime number. So they have numbers in common. So when you have things that are shared, they have things in common. What you do is you add the probabilities, the probability of getting a prime number and then a probability of getting a multiple of 3. And then you subtract out the overlap so that you're not double counting. So we're going to start with a sample space of prime numbers. And we're rolling a die, so we only have choices 1 through 6. So we have 2, 3, and 5, which are prime numbers in 1 through 6. Then multiples of 3 are 3 and 6. Those are the only numbers that are multiples of 3 when you can roll a die. So you can see, I'm going to highlight this, that we have an overlap of 3. So we're going to calculate the probability. So first, the probability of a prime number. So I'm going to just actually write this out. Probability of prime, and then we're going to add in the probability of multiple of 3. And then we are subtracting prime and multiple of 3. The overlap. So we have 3 numbers that are prime out of 6, so it's 3 over 6, plus, and then multiples of 3, there are 2 of them, 2 out of 6. And then we're subtracting, there's only 1 number in cost both, 1 out of 6. So you have 3 out of 6 plus 2 out of 6 minus 1 over 6. 3 plus 2 is 5 minus 1, that's 4 over 6, which reduces to 2 over 3. So the probability of getting a prime number, actually that should say or a multiple of 3. Or a multiple of 3 is going to be 2 out of 3. If you wanted a prime number and a multiple of 3, that's 1 out of 6 because there's only one that fits in both. So you do have to pay attention to whether it says or and. Make sure that you type it correctly for what you want. I wrote and instead of or, but that actually makes a big difference because and means it has to be both, or means it could be one or the other. And so you could possibly double count there. All right, so next is independent events. And so I did mention with the heads and tails that those are independent events. So here's another one that's independent. And independent means that the probability of one doesn't affect the probability of another. So assume the probability of the birth of a child of a particular sex is 50%. In our family of 4 children, find the probability that all the children are boys. So the probability of getting a boy is 1/2, same as probability of getting a girl. And so you have 4 spots you're filling in. And if you're looking for the probability, they're all boys. Since the probability of your second child here, we're assuming has nothing to do with what you got for the first child. So they're independent. So you can multiply these probabilities. So the probability of a boy is 1/2. And then your second child, you still have a 1/2. Third child, you have a 1/2. Fourth child, you have a 1/2. So you just multiply all of these probabilities together. So that gives you 1 to 2 to the 4th power. Or you can also write this as 1/2 to the 4th. Those are exactly the same. And when you simplify that, 2 to the 4th is 16. So the probability of, in a family of 4, having all boys would be 1/16. All right, so now here's my last example, and this is going to be dealing with complements. So a complement of event is 1 minus the probability of something like the event itself. And basically, this would be like if you have a possibility yes or no, the probability of no is 1 minus the probability of yes. So a space vehicle has an independent backup system for one of its communication networks. And independent is important here because that means that the probability of one doesn't affect the probability of the other. The probability that either system will function satisfactorily during a flight is 0.985. So the probability that it works, that one works basically, is equal to 0.985. What is the probability that during a given flight, at least one system functions satisfactorily? So there are 2 ways to do this. We can look at the probability that at least one works, and then add in the probability that, since there's two systems, that both work. Or what we could do is say, okay, if we want the probability that at least one functions, that is 1 minus the probability of none of them working. That's the complement here. So we're going to do it the complement way, especially because it doesn't specifically state that there are 2 systems here. I'm assuming because it seems like you'd have just one backup, but it doesn't actually say there are 2. So we can't actually say probability of 1 or 2, or, we don't know where to end. So we're just going to do the probability that at least one works is 1 minus the probability that none work. So we then need to figure out the probability that none of them work. And again, let's just assume that we have 2 systems here. We have the regular one and then a backup system. So let's just say there's 2 systems. So 1 minus, and the probability of none working. Well, if we have 2 systems, we have 2 spots here. So if the probability of it working is 0.985, we can then find what is the probability of not working, and that's 1 minus that. So again, that's a complement. It works or it doesn't. So you subtract it from 1 because probabilities have to add a 1. So that's 1 minus 985, that gives you 0.015. So the probability none of them working would be the probability of the first one failing times the probability of the second one failing. Because they're independent events, so we can multiply those together. So this is 1 minus 0.015 squared, basically. So you need to square that. And you get 0.000225. So I subtract that from 1. And so the probability that at least one of them working is 0.9997775, which would round to 1, basically 100%. So it'd be very, very slim chance that it would not work, which is why you have backup systems and you make sure that your systems don't fail often. If that was a lower probability, you might want to consider having 3 systems so that you have a smaller chance of having all of them down. So these are some additional examples. I do recommend watching my lesson on 9.7 so that you can get more details on the terminology and all of this, but hopefully this was helpful. And I don't know if you guys have any questions.